Hello everyone, it's November 1st. It's a little bit late today. Let's just get it over with. Find mode in binary tree. Given a root of a binary tree with duplicates, return all the modes, the most frequently occurred element in it. If the tree has more than one mode, return them in any order. Assume a BST is defined as follows. The left subtree contains only nodes with keys. Oh, it's a binary search tree. Less than or equal to the nodes key. The right is greater than or equal. Both the lefts must be binary search tree. Could you do that without using any extra space, assuming that the implicit stack spacing code does not count? Oh, so that's the tough part. I mean, yeah, so the basic idea is you go through everything, but you need to have a counter, right? You need to have a counter to count everything, and then that will be it. But could you do that without using any extra space? Well, we need to take advantage of binary search tree. What does binary search tree do? So you give a root, right? You can check the left or the right, and you're pretty sure, right? If the left and the right, maybe we can chase the same value, right? Maybe we can chase the same value. But you need a result, right? You need to return a result. So you will have to. So you're at the root, okay? And then you look to the left, you look to the right. And they're the same, so you have to keep going, right? And then you look to the left, you look to the right. They are different. So you keep going. How do you do it without using any extra space? Huh. Interesting. Without using any extra space. Like, what if everybody is the same? Oh. They say return them in any order. Oh, no. If more than one mode, return them in any order. So if everybody is different, you have to return all of them. But anyway, you start with the root, right? So everything on the left subtree is smaller or equal to you, and anything on the right subtree is larger or equal to you. And if your left root is already smaller, right? Already smaller. So it is still possible. So it will be possible to create, in this case, it will be possible to create something like this, right? If you have, let's say, 10, and then this one is 5, but this is 10. Like, this is allowed. Same thing here. We can say 20, but this could be 10. Like, this is allowed, right? We need to do a tree visualizer. I want to give it a shot. So 1, 5, and no. Wait, hold a second. 20. Yeah, no, 10, and 10. Right, this one is allowed. In this case, we shall return. Yeah, I'm not returning anything. Not a valley. In Isn't that 5, 10, 10, 10, 20? The left subtree of a node contains, oh, only this one. Okay. That makes more sense. That makes more sense. This is not possible. The only time that you can have repeats is the left subtree of a node contains only nodes with keys less than or equal to the node's key. But still, why is this one not right? The right subtree of a node contains only nodes with keys greater than or equal to. Yeah, why is this not right? Like seriously, why is this one not right? Oh, this is not 1. It's 10. My bad. This is right. Yeah. So then how are you going to do this without extra space? They must use binary search tree, but and it says the stack space doesn't count. No way. Really? You're gonna go there? What if, yeah, I'm just thinking, what if each node returned the number of occurrences of its node? Right? Each node returned the number of occurrences of this node. And each node returns, you DFS it, right? And you return the number of nodes because it says the stack space doesn't count. So we use the stack. At each stack, you return, at each recursion, you return how many 10s there are, how many 5s, how many 10s, right? And then you need to have a result, which is the max count and an array, right? An array. Really an array, not a list. Right? Max count and a list. And you go through the thing, and then once it hits, you just push it in. If it had more, yeah. I think that will work, right? I mean, it will be like what they want, what the problem wants, because the only extra space is the return value, and yeah, it's only the return value and the return value okay. Yeah, the only extra space is the return value, but the return value needs to be there. So we're gonna just say list integer because we have to add to it, right? Modes and max count. Okay. And then private void DFS. Oh, that's not void, that's int. Oh, but how are you gonna know? Ha! You're gonna return a counter. Dude. You're gonna return a counter. Hey, but the implicit stack space incurred due to recursion is not gonna. No, that's not gonna work. That's not gonna work. No, that's not gonna work. Yeah, because you want to count a number of tens. How do you know? Because each one just return a number of that, so you know a number of fives, right? You don't know the number of tens. You have no idea. Huh. Yeah, you have no idea. I have no clue. No idea whatsoever. So let's just solve it and then see the solution. I don't know. I really have no idea. Tree node. Then you need a counter. Right? You need a counter, and you don't need this. You need a counter, which is going to be gonna be a hash map. Yeah, I don't care. Counter. Yeah, but it is, I know, because this I basically didn't use the binary search tree, but I find it difficult to use binary search tree because it's less than or equal to. Like less than or equal to, they can appear anywhere. Right? They can appear anywhere. Well, technically, not really appearing anywhere. You know what? I want to do one more push. Not appearing anywhere. So the same as this must be the right tree on the left subtree. So you go to the left subtree, you just search on the right, right? You search on the right, and you get some. If it's bigger, so it cannot be bigger than that, right? Because if it be bigger than that, you'll be on this. So you go to the left, and then you just keep searching the left, keep searching the right, right? And if the first right, and you just keep going to the right, because the only possibility is on the right. Oh, maybe that's the way, right? You want to find the total number of occurrences of this, because you cannot have the same thing occurring higher. Like you go from the root going down, then the numbers you encounter the first time they show up, right? The first time they show. So each time you go to a node, you want to count how many there are. So you go to its left subtree and you go all the way down the right, right? All the way down to the right. You go right, and if it's equal, you do it again, right? You count. And once you finish counting, So like this is the same. When I counted left subtree, go to the right. Right subtree. What if it's the same? Anyway, if it's larger, then it cannot be on the right hand side. It's only be on the left hand side. If it's the same, then we just do it again. Okay, so we can, but we still have the issue of, do we have the issue though? We have the issue of counting, right? We have this issue of counting. Given the current node, we want to count how many occurrences of this node. So when I traverse, right? When I traverse, if it's the same as this, we just keep counting. If it's smaller, right? 5 is smaller than 10. Then we want to count 5. It cannot happen on the right hand side. No, who said it's not gonna happen on the right hand side? I can have this. It's perfectly legal. I can have this. I can count 5. Who said I cannot? Because it's the left subtree, so as long as this is the right sub, so this has to be larger equal to 5 and smaller equal to 10. And I can perfectly just do 5, 5, 5 all the way down. That's perfectly fine, right? So I cannot say just because it's 5, there's no more 5 on the right subtree. There's still 5 on the right subtree, which means we need to find 5 as well. So my problem is we'll do a lot of repeated, but does that matter? Does that matter if we do repeated traversal? So we're looking for 10, right? And then we say at each node we'll have a target, right? We'll have a target. So we always go left and right. Oh, yeah, you always go left and right, you just have to keep going. No, not necessarily, because if this is smaller than 10, right? If this is smaller, if the current node is smaller than a target, then you can never go on to the left, because the left would just be smaller or equal to, so it would never happen. So you go to the right, right? If it's equal, you have to go both sides. If it's larger, then you only go the left hand side. So by that, you probably won't traverse everything. You will have an early stop. So you will have traverse everything of this. And that's it. But at each node, you do whatever your parent tell you to do. And you have to do yourself, right? You do yourself. So you traverse the left. If you want to do yourself, count how many, like say, how many 5 there is. So you always go both sides. Right, you have to always go both sides because you never know. And then when you go both sides, you keep going. So maybe, because I know how to do it with a counter, and I don't want to do it with a counter. Maybe I can just return back to this, right? And is it a void? And what do we return? Right? What do we return? That's a big question. That's a big question. The return value. We do need to have a return value, right? Because we need to know. So we have a target, right? We have a target. Right? We traverse here. We want to find the count of this target. And then we'll return an int is the total count of the target. Right? Yeah. So when we do this, we'll just call DFS root and then root.val, right? This is gonna give me a root count, right? The count of the root value, how many there are. And we can say, you know, the same thing if root is, I'm thinking like, can we include this inside? Like, we get a ridiculous value, right? Which doesn't matter. So now we can check. Oh man, we have to do one more if, right? We have to do one more if. I kind of don't want to do one more if, so we just do it here, right? So we can say root count is equal to this, right? And we say if root count is larger than max count, then we just return new int root.val. Root is the biggest, right? Else if root count is equal to max count, then modes.add root.val return modes.toArray. Yeah, that's not right. Int res equals new int modes.size for, let's do it in one line. Int I equals to 0, I is smaller than modes.size plus res I equal to modes.get I, and I'll return res. Just realized that's the other one as well. So yeah, okay, now it's just a DFS. Okay, so the DFS, so we want to find a target given the current mode. Then we say if node.val, well, hold a second, if a not node or node is equal to null, return 0. We have no count. Otherwise, if node.val is equal to target, okay? So when node is equal to target, then we need to do DFS node.left target plus DFS node.right target, right? Now we need to say int count equal to 0. Okay, so count can equal to this plus 1 because it's equal to target. So in the current one, and then you do the left, you go to the left, you find the count, to the right find the count, boom, done. That was the count of the target, right? The count of the target. Now if it's not the same, okay, so what is this count? This count is the current, right? We need to have a count of the current, and the count, we'll have two counts, self count and target count. So we have a self count and we have a target count, right? So two things. And what we return is return the target count. Then we say if node.val is equal to target, then self count and target count become the same, right? But we're still gonna call it target count. okay, equals this and this, but target count is equal to self count. So in this case, self count and target count is the same, are the same, right? So what do? We say we have the target count. No, we do a self count. But we're gonna return target count. Dude. Anyway, we're gonna do, can we do target count equal to? Oh, is this syntax legal? Int a equal to b equal to c equal to 1. No, int a, int b, int c. A equal to b equal to c equal to 1. And b, c. Ah, I think it's legal. I think that's legal. Which means we can do this, right? Self count are the same. Else if node.val is, let's say, smaller than target. Okay. Node.val is smaller than target, so the target is bigger. Then target count shall equal to DFS node.write target. Right? That's the target count. It can only go on the right hand side because I'm smaller, it cannot go left. So I have to go right. And self count is equal to DFS node.left node.val plus DFS node.right node.val plus 1. Right? That's the self count. Else node.val is larger than target count. So equal to DFS node.left target, and this is the same. Self count is the same. So with this, we kind of can see, right? We have to do a self count no matter what. Okay, so we have to do a self count no matter what, and then we can int target count and int self count. Self count is going first. If it's this, then this is equal to self count. Otherwise, we have to compute a self count, target count. So once we're done, we have a self count. Then we use self count to handle. So if, say, self count is larger than max count, then what do? We say modes.clear and modes.add node.val. Else if self count is equal to max count, then modes.add node.val. Right? Yeah, and then we'll return target count, because we have a target passing in, which also means that we are going to make some little change. Right, so this is a handle target count. Blah blah blah, and then update molds. So I'm trying to see if this one, because we have this kind of repeats. It should be if it is larger or equal to, right? And then if it's larger, then we clear. Yeah, but if it's smaller, we don't do anything. But okay, so in this case, we can do anything, right? But I kind of don't want to do anything. Root.val, right? So I come in, we do a self count, and then we have a target count. If it's equal, target count is equal. Otherwise, so we do the target. And then we update the nodes, the self count, and then return target count is fine. And let's see. Oh, interesting. It's definitely harder than yesterday's simple problem. Yesterday's medium problem. Oof. Oof. That is not right. That is not right. How come? The first one is wrong. Output 1. All right, so root in root.val is 1. Okay, so target is 1. Self.count, we try left to 1, that's 0. And we try right, is also 1. So we're here, we try 1. And then we do a self count. Left 2, right will be 0. So now here is a 2. Again, we do a self count. Left is nothing, right is nothing, so self count is 1. And target count is the same. Right? Target count is the same. Self count is larger than, so modes not, so return target is 1. So return here, which I call the left, so it's 1. So self count is a 1 plus 1, self count should be 2. Oh, I didn't update. I know why. So if it's this, max count shall equal to self count. That is not 222. What the hell? Didn't we clear it out? That is bonkers. That's fine. Modes.toString. I think there's a toString function. Send output is 2. How come this one gets max count is 1? Huh. That is problematic. That is very problematic. No dot left, no dot right. So it's the first time self count. Okay, if no.val is smaller than target, so target is bigger. Right, so it has to look on the right hand. Yeah, that's right. Otherwise it goes for the left. That is weird. Max count is 1. Alright, so when that is happening, oh, I don't want to debug because debug I have to create a tree. I gotta figure out why. What goes wrong? I'll figure it out. Hold on. I just need to see what happens here. So we're gonna print some stuff. We're gonna print self.count, print node.val target self count. Yeah, I think you cannot do that. We have to do %d, 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 right? Dot format. Actually, I don't know. Java format string. Oh, you call the format function. String.format. Okay, string.format. So string.format. Give it this, and you give 3 values. 1, 2, 3. This should be right. Nope. I'm missing one parentheses. All right, so we have 211. That is correct. And then 211 again. How is that possible? I mean, first one, I can see this, right? This we get 211. And then we'll return target. Huh. Let's try here. Node.val target, not self count, target count. Two, 1, 0. See, that is the problem. So node.val is 2. Target is 1. Oh, I see the bug. Here is the bug. It should be node.val. Yep, I think that is the bug. There we go. There's actually multiple bugs in the original code. That's not the only one. I also forgot to set this. All right, let's give this a shot. Oh. Ah, man. Ah, man. It has to be a set. How is it possible? Exactly. How is that possible? you will have multiple. I don't understand. I cleared it, right? Then self count is the same. You're telling me that shouldn't be. From two different nodes, you have the same count? Huh. Dude, from two different nodes have the same count on two subtrees. Dude, on two subtrees. Like, we're talking about a situation like what? We're talking about a situation like you have a 10, right? And then you got a 5, 5, 5, 5. Nope. Let me do, so on this side you get 2, 5. On this side you get 2, 5 as well. Right? And then you got a 6. Now you cannot get 6 here. Let's say you get a 6 here. And you get a 6 here. Here you count 5. You get 2 5s. Here you count 5. You get 2 5s. So overall, there should be 4 5s. Right? I think this one will be wrong. I mean, this is just way too many. But I can create something that's... so it'll be 10, 5, 5, 5, 6, 5, null. And then we null 2, 3, 4, 5, 6, 7, 8. Let's see if this is what you want. 10, 5, 5, 5, 6, 5, 5, 6. Yes. And this will be... this cannot be 5. 15. Ooh, 15. Then this will be 5. Ooh, it cannot be. It'll have to be bigger. Alright, then what the hell is this? Holy crap. What the hell? So 14. Yeah, you count 14 here. 14, 1, 2 times, 3 times. Right, 14 you have... I see 14 3 times. And 36, 1 time, 2 times, 3 times. 46, 1 time, 2 times, 3 times. Yeah, this is not gonna happen. Whenever you see the first time something occurs is the most like, but it's still there's a... yeah, it's not possible. You cannot have on both sides with this to be the different one. It will always be the same. So, but why would I push 14 3 times? That doesn't make any sense. Okay? That does not make any sense. When we push 14, no matter how many times, the first time when we push 14, and the next time I want to push 14, that means it's already larger, then we should clear the mode. That doesn't make any sense. What did I do wrong this time? Self count larger than. Alright. That's fine. we say if no.val is equal to 14. Oh, just take a look. All right, we just take a look. We say string format. What do we need? I want the max count. No, not max count. I want the modes. The max count, then self count. Okay, so it's a modes.toString max count self count. Just, you know, cannot find symbol. What? I think you put too many. No, not too many. That was right. Hold a second. Cannot find symbol. I don't know. It suddenly didn't work. Cannot find. What? What the hell? What the actual hell is that? Node.val. I don't want to know. %s, 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 %d, modes.toString max count self count. Oh, maybe this. Maybe it's this. Maybe I forgot the. Oh. You got duplicates everywhere. Maybe I should do it on here. 1433. Right? $36. Oh no, 36 is yeah, we do the same thing. Oh, node 36. Oh, what the hell? We hit 14 again. No, I think I know why. I think you just repeated. Yeah, I think I know. I just hit it again. Then you need to notify that a node has been visited before. How? How? How do I notify that a node has been visited before? I have no way to know unless I set. Then why don't you just... It doesn't work, right? I thought this one will work, but it doesn't. Unless, of course, unless we don't do this. We don't do both at the same time. We always just do it once, right? We have no F target, and we always do the target. So we run the target first. Is when we finish run the target, we run itself. We run the target first. We run the target first, so we always say if it's equal, if it's smaller, then we do this. If it's larger, if it's equal, then we run this. Okay? And but self don't count. You run the self. Get 3, right? But how come you run 14 again? You get a 3. That just doesn't make any sense. Like, how can you get 14? How can you get 14 to have 3 again? Like, what the hell is this? It doesn't make any sense. Right? We see this. 14 only appears. That's the only time we appear, right? So we go here, then we say we'll find 14. Then we go here, we get 14. But this 14 should only return 1. And this we have a 14. And that's it. What's the problem? I don't understand. I don't understand it at all. Oh. Let's see. I just want to self count. Okay, that's not what we want. And we have so you're telling me we have visited this node 3 times. We have visited this node 3 times. Yes. First time is, I mean, when you hit this, we visit once, right? And this, visit twice. Yeah. Yep. And probably what's the third time then? But anyway, this one visit multiple times. I see why it does that. How do I notify that we have already done it once? How? I mean, we can definitely use like a set will work, right? That would turn this into a set. It will work, but it's not making things any better. We're having the same problem. Mode doesn't have get. Does modes dot to array? Can we turn a set into an array? Set to array. Something like this. But it's integer. Yeah, I'll be right, but I don't think that's the way to go. It's super slow. It's not gonna work. It's not the best. I mean, we're already using extra space, so we might as well. We might as well. We might as well just set, right? Visited. What's the purpose of doing this, right? It still, baffles me. Might as well just use the other method. if node.val, say visited.has contains, I remember. Right, if that doesn't contain, ooh. Yeah, if it's the same. Dude. You might as well just save it. But if you save it, what's the purpose of using this in the first place? Again, I don't understand. Right? Wait. All right. I don't understand. All right, if you have to go through all this, you might as well just map it. You know? Easy, simple. I don't know how to do it without. Yeah, I'm just give up. That we don't even need all those things. We don't need all those things, so we just don't even consider it. I mean, no, you just don't even consider it. We just return, right? And then we just say not mode, this is a counter. So we say counter.put node.val counter.get node.val get our default 0 plus 1. Just if node not equal to null. Ooh, that's interesting. So you have to go through the counter and find the most. Oh. So you still have to use a list. Oh my god. Modes. We use the same thing. Int max count equal to 0. It's just for. How'd you go through the keys? I think we can say counter dot values key sets entry set. How'd you go through entry set? Java set, no. Hash map entry set. How do you do that? Map.entry, or for map.entry integer entry of this. If entry dot get value is larger than max count equal to entry dot get value modes.clear, modes.add. Entry dot get key. Else if entry dot get value is equal to max count, then modes dot add entry dot get key. Then we handle the rest. That is very interesting. Missing values. Oh, I forgot to. You forgot to. It's getting late. That's why. I forgot to traverse. But still, the problem remains. Right? How do we do it without? I couldn't figure it out. Cannot figure out how to solve this problem without extra space. This solution uses extra space to count the number of nodes, which essentially does not use the binary search tree clue. I don't know, I mean, we tried. It's not like we haven't tried. We tried, but it didn't work. But we have to make directory. All right, show me. No, yep. That's true. You sort this tree. Really? Oh, you sort the tree. And then they will all be one after the other. Oh. Oh, I think I know. You saw the tree and just go through them. Holy crap. Oh, yeah. No, I have to admit, yep, I didn't think about it. So, okay, we'll do it. We'll do it. You just in order it, all right? You in order it, and then you compare to the previous one. That's all we need. That is all we need. We do need a list for the mode. Mode. right? We need a max count, current count, previous value, and then we'll DFS, right? If node is not equal to null, we're always right, then we always dot left DFS, no dot left, and then we do the current one. We say DFS dot, not DFSs, no dot val. If no dot val is equal to pre, current count plus plus. If current count larger than max count equal to current count, modes dot clear, modes dot add node dot val. Right, that's that. Else is not equal. Oh, actually, we don't do this here. We just, so we don't have to do it multiple times. Yeah, we don't do it here. So if it's equal, we just count. If it's not equal, then we say if current count is larger than this, then we don't add no.val, we add pre, right? And then always current plus plus, right? So we say pre equal to no.val, and then current dot plus plus. Oh, hold a second. We have to say current count equal to 0, and then current dot plus plus. So this shall be if is not equal to, right? If it's not equal to pre, so it's different, then we check the current count. If current count larger than, we'll add the previous count. Else, if current count is equal to max count, then we'll just add the pre. Once it's done, reset, do this. Okay. Once it's done, then we do DFS no.write. I can't believe I didn't think about this. With a healthy dose of hint. Yep. I cannot believe I forgot about the one of the most important characteristics of binary search tree. In order traversal leads to sorted values, and we can keep counting the number of repeats in a sorted fashion when performing inorder traversal. In this case, we do not need any extra space except for the space needed to record the current modes. Ooh, that was the first one. Did you forget to update? No. Interesting. We have one. Oh, the current count. Okay, that's why I put one in. And then pre shall equal to 2 now. Current count is 1. Oh, I think you forgot to handle the case. No. It's at the end, you have to do it one more time. You have to do this one more time. Right? Once we get out, we just need to check if current count is larger than max count. Then we'll return new int pre. Else if current count equal to max count, modes.add pre. Yep. That's the way. No, it's not. It's not. It's yeah, it is easy, but took a very long time. I did not realize that, honestly. Did not realize about the no value at all. Come on. Oh, but this one still has on. Oh, the Morris traversal. You loop it back, right? Yeah. No, you still have to use this. But that's just the answer, I think. Yeah, you have the reset answer. That's exactly the same. I don't even need this. I don't even need Morris. I didn't find reset though. Where is reset? Yep, here. Answer equals to new. They basically don't reset. They just get a new one. Now, you don't need that because you can traverse it doing at the same time. You don't need Morris traversal. You just keep track. I don't know why you need Morris traversal. I think, wait, what does the Morris traversal do? Reshape the tree. Oh, it's no recursion stack. This one requires recursion stack. Morris will not require more. Yeah, I think it's the rightmost pointing back to the root, right? So we'll go here and go here. So we need a link back. Yeah, so you go to the left, go all the way to the right, pointing back. Because this is the last node. For this left subtree, this is the last node. So you go here, go all the way there, create the link, right? Create the link. So once you finish, you can go back. And then you go here, same thing, go all the way down, but you will end up with 3 pointing back. Yeah, so every time you go the left subtree, you always go as right as possible and pointing back. So you have a 3 new pointing back, this new pointing back, this new pointing back. Yeah. Now we can go back. Yep. That's it. True. That's Morris. I still remember. It's just not really wanting to implement this. I mean, this is a hint, right? If left is not no, get to the left. This was in the C++, the first C++ class I have. and Miles. I think Professor Wiles. You go left, and then you just keep going right as you can. Once you go to the root, no, the leaf, you will current dot delete the edge. They're using it. Oh, you have to delete the edge that you're currently using it. Really? Why? Why do you have to delete it? Oh, because you go back here. You don't want it to go left again, so you have to delete it. So you will go right. Yep, you have to delete it. And the current you go to the left. Yes. You try it again, and then you can do this. Yeah, this is just the same. Oh yeah, this is the same, right? This is the same. The only difference is the traversal itself becomes Morrison. And there's a way to put it back. Yeah, I don't want to know. I do not want to know. All right, that will be it. It's actually a good journey. I haven't thought about Morrison traversal for a very long time, and inorder. I haven't even thought about inorder for a very long time. All right, I'll see you guys tomorrow. Adios.